Hey, what's up, guys? So today I'll talk about this famous lower bounds of Graver's algorithm, and I think this result is interesting. So it's very good for me to make a video and describe how it goes. Okay, so let me just first recall that in the usual task that we start from, let's say we have 0, 1 up to -1. We have a function from 0, 1 up to the -1, and then let's say back to 0 and 1. And there is only x. There is a particular x such that f of x 0. And we just use the different notation. So this f of y. So x is our answer. So only particular x. So this means that it's 1 if y is x. Otherwise, that is 0. Okay. So our task. Is to find x. Okay. So if you use the simple classical theory, will give you the omega and lower bounds. And then if you use a quantum, which is a Graver's algorithm, we can give you the square root of n. Okay. Okay. So our goal is to show like the square root of n is optimal. Okay, so that means that you cannot, let's say, you cannot go to that 1/3, or you cannot go to like 3 divided by 7. This is not optimal. So square root of n is really the optimal way that one can do it. Okay, so the Graver's algorithm will use the oracle. Okay, so you will in the Graver's algorithm, one will define oracle O of x, which act on a particular state y be minus f of O will OXY will be let's say f of y. Okay. So y, if y is not the same as x, then the O of y will be just y. Otherwise, O of xy, OY of x will be minus x. Okay, so this is the Graver's algorithm. Basically, you just make some combination and view as a rotation, and you can get a square root. Okay, so the question is that why square root of n is optimal. Okay. So let me just go to the proof. So the idea is that imagine that this is your initial quantum states psi, and then you do something. You do some Curie, and then you do some unitary. You want, and you do some Curie, and then you do some unitary, and keep going. Okay, and then let's say up to L stage, which means that OX and the UL, which is unitary, so up to L stage. Okay, let's say this is your final state. Let's call it psi LX. So this is ULOX, ULX1OX up to U1OX. Okay, so and then we want to say that this psi LX has large enough amplitude. Okay, so we want X inner product with this psi LX should have the higher probability, right? Should be constant probability. So we want these terms to be, let's say, greater or equal to half. This is our first requirement. Okay, and then we want to claim that in order to do this, the number of OX should goes to like square root of n. Okay, so this is like our proof. So that means that you at least need to do a square root of n to make this overlap greater or equal to half. So usually, if you start from this side to be the linear Euler superposition, then the particular side amplitude will be 1 over n. So we need to start from 1 over n to go to 1 over half. So go to half. Okay, so we need to increase up to half. And then we want to prove that the number of OX, the mirror number of OX is basically square root of n. Okay, then one can define our psi L, which is you don't use any oracle. Okay, We don't use any queries. Okay, so one can define is phi L to be summation of x by psi L x minus psi L. Okay, so sometimes I will use this, sometimes I will use this, but they are the same. Okay, square. Okay, we want to prove this phi of L. We want to prove the two things. Okay, so this first one is this phi of L is greater or equal to big O of n. And the second one is this phi of L is less or equal to 4L squared. Okay, so subject to the condition. So subject to the condition and what we previously required. Okay, so once we have this, then obviously that one can prove that one can see that the 4L squared is greater than O of n. So L is greater or equal to O of square root of n. Okay, so phi L is somehow like the middle stage that we can make this L consider the approach to this n. So phi L is like an intermediate step. Then one can use this to find the bounds. Okay, so proof. Let me just prove one. Okay. So proof one is simple. So let's write phi L to be summation of x phi L x minus phi L squared. Okay, and then you can simply show this. It's just basically summation of x phi L x minus x plus x minus phi L squared. So this is exactly x phi L x minus x squared plus x and x minus psi L squared, and also this inner product. Okay, but I can just make it greater or equal to, and then minus 2 with the inner product with the length of the inner product. Okay. So this is basically the Cauchy-Schwarz. Okay. And done. Okay. Okay. So let me define AL. Let me define AL to be just convenience for the first time, for the first term, and then we define BL to be x minus phi psi L squared. Okay. What's going on? Okay. So the one can check these terms. Okay. So obviously that these two. Okay. So then we just use Cauchy-Schwarz. CH. So Cauchy-Schwarz tell me that this x is phi L x minus psi L can be viewed as a two product. Right? So this guys can be viewed as a vector of first coordinate, second vector, and the two linear products. So this guy square root of that, so you can do summation x and square x minus phi L squared. Okay. So this is AL and the BL. Okay. So this term is greater or equal to AL squared AL plus BL, and then these terms is less or equal to minus 2 square root of AL BL. Okay, so this is square root of AL minus square root of BL squared. Okay, so this is our lemma. So we express this phi L in terms of square root of AL minus square root of BL. Okay. So the next thing we want to say is that we want to go to find this AL and the BL. Okay, we want to find these two terms, and once we done this, then we should be able to use this expression. Okay, so step one is to find AL. So let me just write AL. AL is summation x psi L x minus x squared. Okay, so remember that we subject to this condition. Okay, so hopefully this is simple, right? Because you can just write AL in terms of x. Right? So this gives you 1 plus 1 because they are unit vector. So it's 2, 2, right? And minus, maybe do step by step. Okay, so it's psi Lx minus x, and psi Lx minus x. So it's x1 minus psi Lx x minus x psi Lx 1, the summation of x2 minus psi Lx minus x psi Lx. Okay, so I can write these terms. Some radius r is exponential I theta r greater or equal to 1 over square root of 2. Okay, so if you do this, you get summation of x2 minus, if you plug r exponential I theta, so for these terms, in these terms, you get r cosine theta. Okay, and the summation x is independent. This term is this term is less or equal to, right? So less or equal to n and 2 minus. So I want to make since x can be arbitrary, right? So I can make cosine to be, let's say, 1. Okay. So should be this. Right, 2 minus square root of 2 times n. Okay, because this x can be arbitrary, so I shouldn't require x to be, I shouldn't require theta. Okay, so I use 2 minus 2r. Okay. Okay, so this is our AL, and then our step 2 is find BL. We got BL. Okay, so step 2. So let me just write this. So we get x minus L squared. This is our goal. Find this one. Okay, so let's write phi to be ax, the x or particle x. Search for any x, and one can just write x in terms of so these terms only x is difference, right? So you get summation ay squared plus 1 minus ax squared. Y do not the same as x. Okay. Okay, so you can make the first term, then make the second term to be x. I do not the same as x, ay squared, but add one term. So I can add, let's say I add ax squared. So I need to minus the term here. Okay. So for each x, I get y different from x, and I add ax terms and minus ax terms. Okay. So it should look like this. Okay. So obviously that the first term is the same, and this one will give me n. This one will be 1, right? Because this one will be 1. Right. So should be this. So this term will give me 1. So okay, n minus 1. Okay. So one can write it as 2n minus 2 x ax absolute value. Okay, and then using Cauchy-Schwarz. So since I know that ax squared x is 1, so I'm using Cauchy-Schwarz. I get x is that's equal to square root of n. Okay, so this is capital N. Okay, so I get these terms is greater or equal to 2n minus square root of n. Okay. So there's a 2 here. So 2n minus 2 square root of n. Okay, so let me just go back to here. So let me just write down. So what we prove is that the phi L is greater or equal to, let's say AL minus square root of BL squared. And I know that AL is bounded above, and the BL is bounded below. So BL is bounded by 2n minus 2 square root of n, and this is 2 minus square root of n. Okay, so simple calculation, where you take a square roots and then you choose make a difference. So you can prove that the phi L greater than big O of n. This is a simple calculation. You just plug it in the square. Okay. So you will see that the leading order terms big O of n. Okay, come from since you take the square root and you also square. Okay, so let's prove that. Okay, so now let's prove the lemma. Let's prove the 2, which is this phi L is less or equal to 4L squared. Okay, so this is done by recursion. So I can write this basically OX by psi LX minus psi L squared. So I can write summation X OX psi LX minus OX psi L plus OX psi LX minus psi L squared. Okay, let's equal to X, the OX psi L X minus psi L squared plus X, and I replace the cross term to be the magnitude. So I get OX minus I psi L plus X OX minus I psi L squared. Okay. Okay, so I want to bound this term, right? So this term is exactly so let me just write this. Sorry, so this term is OX psi L squared is less or equal to X. And the magnitude of O. So magnitude of O is 1. Okay. Psi L squared. This is exactly phi L. Okay, so this term is phi L, and the next term, this term is square root of phi L, and this OX minus will give you another 2. So get 4 square root of phi L. So the crazy idea is the final term. Okay, I want to bound the final term. So how should I bound it? Okay. So how should I bound these terms? Okay, so you can just insert it with a unitary term. Okay, so you can prove these terms actually is. Well, you can insert the unitary because remember that this psi L and the psi LX are all differ by a sequence of unitary at oracle. So you can make all the unitary here and plug it into this and become this. Okay, and this is guys actually less or equal to 4x and x psi LX squared. Or basically, I guess that you can prove this. Just start from here and do here. Okay, so you can prove this. I think without using it, just directly square it and then prove it. Okay. So which is 4. Okay. This is almost trivial, right? OX minus I, right? So there are differences. You can prove it's actually 4. So this is 4. Okay. So what we have proved is that it's phi L squared is equal to phi L. Sorry, phi L plus 1 is equal to 4. So phi L squared plus 4 phi L plus 4, which is phi L plus 1 squared. Okay. So anyway, I claim that phi L is less equal to 4L squared. So for L equals 0 is trivial. 0. I can prove my mathematical induction, so I can check phi L plus 1 squared is actually less or equal to phi L plus 2. Plus 2 squared. So it's okay, so it's less or equal to 4L squared plus 2 squared, which is exactly 4L plus 1 squared. Okay, so hopefully it's true. Yeah, it's true. Okay, so done. Okay, so finish. Okay, so because what we have proved is that phi L is a greater or equal to big O of n, and phi L is less or equal to 4L squared. So we prove that L is greater than O of square root. This proved the this proved the Graber's algorithm is up. Okay, that's it. See you guys next week.